Welcome back to Stellar Terrors, where we explore the most mind-blowing ideas in space science in a simple, engaging way. I'm your host, Alexa, and I'm so glad you're here with me today. In this episode, we're asking a question that's fascinated me since childhood. What if humans actually tried to live on Mars? Not just visit, but build homes, grow food, and survive on another planet. Is it possible or completely unrealistic? To break it down, I'm joined by aerospace scientist Eric Riley, who has spent decades studying life on Mars. Let's dive into the science, the risks, and the reality of making Mars our second home.
Alexa, thank you so much. I have to say, slightly space obsessed is the most polite way anyone has ever described this particular audience. I have a feeling they're deeply, passionately, possibly alarmingly space obsessed.
Okay, deeply and passionately, yes. Alarmingly, I'll let them speak for themselves. But Eric, I'm so glad you're here. I want to get into absolutely everything today, and I mean everything. The good, the nightmarish, and the I can't believe humans are actually considering this.
That's exactly the right frame for this conversation, because the answer to can humans live on Mars is not a simple yes or no. It's a yes, theoretically, eventually, but the path to get there is filled with challenges that would test the limits of human engineering, biology, psychology, and political will. In other words, it's a great podcast topic.
It really, really is. All right, let's start from the beginning. Let's start with Mars itself, because I think a lot of people have an image of Mars in their heads. The red planet, dusty, kind of like a desert. And I want us to shatter that comfortable image right at the top. Eric, describe Mars to us. What are we actually dealing with?
Right, so let's set the scene. Mars is the fourth planet from the Sun, roughly 227 million kilometers from the Sun on average, which means it's about 1.5 times farther from the Sun than we are. And that distance matters enormously for temperature. The average surface temperature on Mars is around minus 60 degrees Celsius. Minus 60. Now, before anyone thinks, well, that's cold, but Antarctica gets cold too. Yes, but at the poles in winter, Mars can reach minus 125 degrees Celsius. And even at the equator during a summer afternoon, you might hit a brief, glorious high of about 20 degrees Celsius. But then the night comes and it drops to minus 73 in the same spot, same day, same location. So the temperature swings on Mars are violent. Your engineering has to account for that constantly.
That's already terrifying, and that's before we even get to the atmosphere, right?
Right, the atmosphere. This is where it gets really stark. Mars does have an atmosphere, but it is barely there. The atmospheric pressure on the Martian surface is about 0.6% of what we have on Earth. To put that in perspective, it's roughly equivalent to being at an altitude of about 35 kilometers above Earth. No human being can survive in that without pressurized protection. You would not just struggle to breathe. Your blood would begin to boil. Your lungs would rupture. You would be dead within minutes. And the composition of that thin atmosphere? About 95% carbon dioxide, about 2.6% nitrogen, about 1.9% argon, and a mere 0.13% of oxygen. We need about 21% oxygen to breathe comfortably. Mars gives us 0.13%.
Okay, so you can't breathe outside, you can't stand the temperature swings. What else? Because I feel like we're building to something.
We are. The next major factor is radiation. Mars has no global magnetic field, or rather, it has a very weak, patchy remnant of one. Earth's magnetic field is like a giant invisible shield deflecting solar wind and cosmic radiation. Mars lost its magnetic field billions of years ago, likely because its core cooled and solidified. Without that shield, the Martian surface is bombarded with radiation, solar energetic particles from the sun and galactic cosmic rays from deep space. The radiation levels on the Martian surface are roughly 200 to 300 times higher than what we experience on Earth's surface. Long-term exposure at those levels significantly increases cancer risk, can cause radiation sickness, damages DNA, can affect cognitive function. This is not a problem you can fully solve just by being careful. You need shielding, constant, structural, significant shielding.
And then there's the dust, right? I know Martian dust is not just like regular annoying sand.
Not remotely. Martian dust is extremely fine, much finer than sand. It's made of iron oxide, rust essentially, mixed with perchlorates. Perchlorates are chlorine-based compounds that are toxic to humans and disruptive to thyroid function. This fine perchlorate-laced dust gets into everything. It coated the solar panels on the Opportunity rover. It can block out the sun during the planet-wide dust storms that Mars experiences roughly every few Martian years, storms that could blanket the entire planet in a reddish haze for months. Those storms would reduce solar power generation dramatically. If you were relying on solar panels, a global dust storm could be catastrophic.
Wait, planet-wide dust storms? Like the entire planet gets covered in a dust storm?
The entire planet. We saw this happen in 2018 with the Opportunity rover. A global dust storm developed, blocked out the sun for months, and Opportunity, a solar-powered rover, never woke up again. It had been operating for 14 years. The storm ended it in weeks. Now imagine that storm hitting a human colony that depends on solar energy for power, heating, food production, everything.
That is one of the most chilling things I have heard in a while. And these storms, you can't predict them well enough to just prepare?
We're getting better at prediction, but we cannot predict them months in advance with the precision we need, which is why any serious Mars colonization plan has to think far beyond solar power as a primary energy source. Nuclear is almost certainly part of that answer. NASA's Kilopower project has been developing small nuclear fission reactors specifically for this purpose, compact, reliable, not dependent on sunlight.
Segment 3. The journey. Getting to Mars. Approximately 7 minutes. Okay, so we've established that Mars is, in many respects, trying to kill you just by existing. But let's back up, because before you even deal with all of that, you have to actually get there. And I think people underestimate what that journey is like. Talk me through the trip.
The journey to Mars is one of the most medically and psychologically demanding experiences a human being could undertake. Let's start with time. Depending on where Earth and Mars are in their orbits, they align favorably roughly every 26 months, which we call a launch window. A one-way trip to Mars using current propulsion technology takes between 6 and 9 months. Let's call it 7 months as a working average. 7 months in space.
7 months. Just floating there.
7 months in microgravity, which means essentially zero effective gravity. And microgravity is extraordinarily hard on the human body. Your bones begin losing density almost immediately, about 1 to 2% bone mass per month. Astronauts on the International Space Station who are in microgravity for 6 months can lose up to 10% of their bone density. Your muscles atrophy, your cardiovascular system weakens because your heart doesn't have to work as hard to pump blood against gravity. Your vision can actually change. We believe this is related to intracranial pressure shifting in microgravity. And that's before we even get to the radiation exposure during the journey. In transit, you're no longer shielded by Earth's magnetic field or atmosphere. The Curiosity rover's radiation assessment detector measured the radiation dose for a round trip to Mars at roughly 1.01 sieverts. That's about a 5% increased lifetime risk of cancer just from the journey, both ways. That's above NASA's current radiation limits for astronauts.
So you arrive on Mars already weakened. already irradiated, already having spent 7 months in a tin can with the same handful of people.
Exactly, and the psychological dimension of that cannot be overstated. There are studies of long-duration mission simulations, the High Seas mission in Hawaii, for example, where crews lived in dome habitats in isolation for months at a time to simulate Mars missions. The findings consistently show tension, communication breakdowns, sleep problems, depression, and what researchers call third quarter phenomenon, a dip in morale and performance that hits roughly three-quarters of the way through a long mission. The isolation, the confinement, the monotony, these are real threats.
And on top of the psychological pressure, you can't call home easily, can you? Like there's no quick phone call to your family.
Right. This is something people often forget, the communication delay. Because of the vast distance between Earth and Mars, radio signals, which travel at the speed of light, can take anywhere from 3 to 22 minutes to travel one way. So at the worst alignment, a message to Earth takes 22 minutes to arrive, and the reply takes another 22 minutes to get back. A conversation that would take 2 minutes on a phone call takes nearly an hour. You cannot call mission control in an emergency and get instant advice. You are, in many respects, on your own.
That is genuinely terrifying to me. The idea that if something goes wrong, you send a message and you just wait 44 minutes for an answer that might not even solve the problem.
It means that Mars colonists must be extraordinarily autonomous. They must have deep expertise across multiple disciplines: medicine, engineering, geology, biology. You can't be a specialist who relies on a support network. You have to be something much closer to a Renaissance scientist who can also fix a life support system in the dark. That changes who gets selected, how they're trained, and how the entire mission is structured.
All right, so you've survived the journey, you're on Mars, you land. What happens next? Where do you live?
The first question, the most urgent question, is shelter. And this is where the design problem becomes extraordinarily complex. You need a habitat that does several things simultaneously. It must maintain atmospheric pressure at Earth-like levels, it must block radiation, it must withstand temperature extremes, it must be airtight, and it must be able to be assembled, at least partially, by a small crew who just endured a 7-month journey and are physically weakened. The most discussed early solution is prefabricated modular habitats, structures sent ahead of the crew, landed on the surface, perhaps partially deployed by robots before humans arrive. These would likely be underground or covered in Martian regolith, the rocky soil, because a thick layer of regolith provides excellent radiation shielding.
Underground Mars bases. That's very sci-fi in a very real way.
It is, but it's also probably the most practical solution. The subsurface provides thermal stability and radiation protection. There are also lava tubes on Mars, ancient volcanic tunnels that could potentially be very large, structurally sound, and naturally enclosed. Lava tubes on the Moon have been mapped at over a kilometer in diameter. Martian gravity is lower, which means Martian lava tubes could be even larger, potentially city-sized enclosed spaces. Sealing and pressurizing one of these would be a massive engineering undertaking, but the potential volume is extraordinary.
That's a fascinating idea. Okay, so once you have a shelter, what are the life support systems that have to keep running every single second? Because I know that's where a single failure can become catastrophic.
Absolutely. Life support on Mars is not a background system. It is the system. Everything else is secondary. You need to continuously supply breathable air, that means producing oxygen and removing carbon dioxide. NASA's MOXIE experiment on the Perseverance rover has been demonstrating that oxygen can be extracted from Martian CO2 through a process called solid oxide electrolysis. The experiment has successfully produced oxygen on Mars. That's a genuine proof of concept. But a MOXIE-scale device produces a few grams of oxygen per hour. A single person at rest needs about 550 liters of oxygen per day. Scale that up for a crew of 6 for a 2-year stay, you're talking thousands of times the capacity of the current Moxie device. The scaling challenge is enormous.
And water? Because humans are mostly water, we need a lot of it.
Water is actually one of the more tractable problems on Mars, and that's exciting. We now know with high confidence that Mars has significant water ice at the poles, yes, but also under the surface at mid-latitudes, closer to where a colony would likely be located for temperature reasons. The Phoenix lander confirmed subsurface water ice in the northern polar region. Radar data from the Marsis instrument on Mars Express has suggested the possibility of liquid water brines deep below the surface, and water can also be extracted from the atmosphere through specialized systems. So water ice is likely accessible, but extracting it, melting it, purifying it, recycling it, that takes energy and infrastructure. Nothing on Mars comes for free. Every resource requires a system, every system requires power, every power system requires maintenance.
So everything on Mars is like a chain, where if one link breaks,
You can find yourself in serious trouble very quickly. That's the nature of closed-loop life support. On Earth, if your plumbing fails, you go to a neighbor or a shop or you call a repair person. On Mars, your plumbing is also your survival system. There's a concept called ECLSS, which is what NASA uses on the ISS. The ISS version recycles about 93% of water used on board. A Mars colony would need to push that to above 98 or 99% because resupply from Earth is impossible in real time. You cannot afford waste. And this extends to food, air, heat. Everything must be captured, recycled, reused, and lost as little as possible. The engineering vision for a Mars colony is essentially a closed ecological loop, more like a spaceship than a city.
let's talk about food. Because I want to know, are we eating protein bars for the rest of our lives on Mars, or can we actually grow food?
Food production is one of the most fascinating and genuinely hopeful challenges. Early missions would likely rely heavily on pre-packed, long shelf-life food, specifically engineered for nutrition, compactness, and calorie density. But for permanent settlement, for a colony, you absolutely need to grow food on site. You cannot ship enough calories to Mars to feed a growing population. The math simply doesn't work. So you need agriculture. And this means indoor controlled environment agriculture. Think vertical farms under artificial light in pressurized growing modules. You would use hydroponics or aeroponics, growing plants without soil in nutrient-rich water solutions. The Martian regolith itself is actually fairly inhospitable to plant growth. It contains perchlorates, which are toxic to plants, and it lacks the organic matter and microbial ecosystems that make Earth's soil fertile. You'd need to remediate it significantly, or just skip soil entirely. The plants best suited to early Mars agriculture would likely be calorie-dense, fast-growing crops: potatoes, sweet potatoes, wheat, soybeans. There's been research into exactly this. The potato has become something of a symbol of Mars food research, partly because of the Martian, yes, but partly because it genuinely is one of the most calorie-efficient crops per square meter you can grow.
So the movie got something right?
Parts of it, yes. The broad idea that you can grow food in Martian conditions is legitimate, though the specific execution in the film skips over a lot of the challenges. The dust storm that kicks off the story would actually not be nearly as violent as depicted. The Martian atmosphere is so thin that even hurricane-speed Martian winds have very little force. But the spirit of science your way out of the problem, that part is extremely relevant.
I want to go deeper into what Mars actually does to human bodies over years, not months, because there's a difference between can you survive a 2-year mission and can you actually live your whole life there?
This is where the science gets both fascinating and genuinely uncertain, because we simply don't have long-duration data for humans in partial gravity. Mars has 38% of Earth's surface gravity. The ISS gives us excellent data on zero gravity. Earth gives us data on 100% gravity. Mars is 38%, and we have almost nothing from that specific level. What we can extrapolate is concerning. We know that lower gravity means your body doesn't have to work as hard to support itself, which means muscles and bones adapt and weaken. Whether Martian gravity is enough to prevent the worst effects of microgravity, or whether it's just a slower version of the same deterioration, we genuinely don't know. This is one of the most critical unknowns in Mars colonization biology.
And what about long-term radiation? Because we talked about the journey, but you're also on the surface being irradiated every day for years.
A Mars colonist living on the surface, even with some shielding, would receive roughly 20 to 30 times more radiation than a person living on Earth's surface. Over a lifetime, that translates to significantly elevated cancer risk. Some estimates suggest that someone living on Mars for 20 years could accumulate a radiation dose that would increase their lifetime cancer risk by 10 to 20 percentage points above the Earth baseline. Underground habitats mitigate this substantially. A meter of Martian regolith, or rock, provides meaningful shielding. But colonists still need to go outside, conduct EVAs, extravehicular activities, to maintain equipment, conduct research, build infrastructure. Every EVA is a radiation exposure event.
What about reproduction? Because a real colony, by definition, has to have children eventually. What do we know about pregnancy on Mars?
Almost nothing, and that almost nothing is itself a major problem. We have never studied mammalian reproduction in partial gravity or in high radiation environments in any meaningful way. Some rodent experiments in space have suggested potential complications, but the data is extremely limited. We simply do not know whether a human embryo can develop normally in Martian gravity. We don't know whether the radiation environment would cause unacceptable rates of developmental abnormalities. We don't know whether children born on Mars would develop normally, or whether a Martian-born child who returned to Earth would be able to function in Earth's gravity.
That's staggering to me, that the question of can humans actually reproduce on Mars is just open, unanswered.
It is, and it's ethically complex. To answer that question experimentally, you would have to be willing to have human pregnancies on Mars knowing the risks are unknown. That raises profound ethical questions. Do you have the right to raise a child in an environment where we don't know the health implications? These aren't science questions alone. They're philosophy, ethics, law, and human rights questions.
And the immune system. What happens to immunity in space or on Mars?
The immune system is dysregulated in space. Studies on ISS astronauts show that certain immune responses are suppressed while others are overactivated. Dormant viruses, Epstein-Barr, herpes simplex, varicella zoster, reactivate in the space environment, likely because of the immune dysregulation and the stress response. On Mars, the combination of radiation damage to DNA, immune dysregulation, and the complete absence of Earth's microbial environment, that last point is something people don't think about, creates a genuinely novel biological situation. On Earth, we're constantly exposed to a vast diversity of microbes. This exposure trains and calibrates our immune systems. On Mars, in a sterile, closed habitat, that microbial diversity disappears. What that means for long-term immune function and even mental health, because the gut-brain axis and microbiome are deeply connected, is unknown and potentially serious.
Eric, we've spent most of this episode cataloging everything that could go wrong, everything that's unknown, everything that's terrifying about living on Mars. So I want to ask you directly, why? Why should humanity do this? Make the affirmative case.
I've been waiting for this question, because despite everything we've discussed, and none of it is exaggerated, it's all real, I believe the case for Mars colonization is one of the most important cases that can be made for any human endeavor. Let me give you a few reasons. The first is existential insurance. Earth is our only home. and Earth is fragile in ways that are both natural and human-made. Asteroid impacts, the same kind that wiped out the non-avian dinosaurs, are a statistical certainty over long enough timescales. Supervolcanic eruptions, pandemic pathogens, climate change, nuclear war. The mathematics of survival suggest that a species confined to one planet is fundamentally vulnerable. A multiplanetary civilization is a civilization that cannot be wiped out by a single catastrophe. Mars is an insurance policy for consciousness itself.
The backup drive for humanity.
Exactly that. Elon Musk uses this framing constantly, and regardless of one's views on him personally, the underlying logic is sound. If humanity is a light in the cosmos, spreading that light to more than one world is simply the rational thing to do. The second reason is scientific discovery. Everything we have ever learned about the history of our solar system, about the origins of life, about the conditions that allow planets to evolve, all of that knowledge has changed how we understand ourselves and our place in the universe. Mars exploration has already overturned assumptions. The discovery of ancient river deltas, lake beds, organic molecules. Mars is telling a story. We've only read the first few pages. A human presence on Mars with the ability to drill, to explore caves, to sample the deep subsurface, that presence could answer the most profound question in science. Has life existed anywhere other than Earth?
And if the answer is yes, even microbial life, ancient fossilized life, that changes everything we think we know about the universe.
It changes philosophy, religion, biology, cosmology, everything. The Fermi paradox, why haven't we detected other intelligent life, gets recontextualized entirely if we find that life independently arose on Mars. It means life is not impossibly rare. It means the universe is probably teeming with it, and it means we are part of something vast and ongoing. The third reason, and this one is perhaps the most human, is that exploration is what we do. From the first humans crossing land bridges to unknown continents, to Polynesian navigators crossing the Pacific in outrigger canoes, to the European age of exploration, to the Apollo missions, humans move. We are driven, perhaps by something deep in our evolutionary psychology, to go beyond the horizon. Mars is the next horizon. And historically, the civilizations that have gone beyond their horizon have grown in ways that those who stayed behind could not have predicted.
And the technology developed to get humans to Mars, doesn't that feed back into life on Earth?
Without question, the Apollo program's technology transfer to Earth, computing, material science, water purification, medical imaging, scratch-resistant lenses, memory foam, has been estimated to have returned multiple times the investment in economic value alone. The challenges of Mars will drive innovation in closed-loop ecological systems, renewable energy, radiation medicine, psychological resilience, sustainable agriculture, all of which have direct applications to Earth's most pressing challenges. We might develop the tools to feed a growing Earth population, manage climate, and improve human resilience precisely because of what Mars demands of us.
Eric, we are coming to the end of what I think has been one of my favorite episodes of Stellar Terrors ever. I want to ask you one final question. You've spent most of your career on this. You know more about the challenges than almost anyone. Do you genuinely believe, that humans will one day live on Mars?
I do. Not because I'm an optimist by nature, I'm actually a fairly cautious scientist, but because of the direction and the pace of the technology. When I started in this field, sending a spacecraft to orbit Mars was an achievement. Now we have rovers the size of SUVs doing chemistry experiments on the surface. We have a helicopter flying on Mars, Ingenuity, which was supposed to do 5 experimental flights and ended up doing over 70 before its blades were damaged. We have private companies building fully reusable heavy-lift rockets. The trajectory of progress in the relevant technologies is extraordinary. Will humans live on Mars in my lifetime? I hope so, but I'm uncertain. Will humans live on Mars in the lifetimes of people listening to this podcast right now? I think that's genuinely possible. Will a human civilization exist on Mars a century from now? I believe yes. Not easily, not without tragedy and setback and loss, but yes.
That might be the most hopeful and terrifying answer you've given today, and I mean that as a compliment. Eric, thank you so much for being on Stellar Terrors. This has been an absolute masterclass. Red World, Real Risks is the book. Please go read it. Eric, where can people follow your work?
My research and writing are available through the usual channels, and I'm always happy to hear from curious people who want to go deeper into any of these topics. Thank you, Alexa, and thank you, Stellar Terrors listeners. The fact that 8,000 people care enough about these questions to spend an hour on them, that's its own kind of hope for the future.
Okay, before I let you all go, your listener challenge for this episode. I want you to imagine you have been selected for the first permanent Mars colony. You can bring 3 personal items, things that fit into a single bag. What do you bring? Leave your answer in the comments or tag us on our socials with hashtag #StellarTerrors. I'll tell you mine. A physical copy of my favorite novel, a handwritten letter from my mom, and seeds. Seeds of something that grows fast and smells like Earth. Thank you so much for listening to Stellar Terrors. If this episode moved you, made you think, or made you stare at the night sky a little differently, please share it. Tell one person, because these conversations matter. Science matters. Curiosity matters. I'm Alexa. This is Stellar Terrors. And remember, the universe is terrifying, and that's exactly why we love it. See you among the stars.